Okay, let's look at one of these ways that we can prove two triangles are congruent by not having to prove all the sides are congruent. Okay, one of these ways is called side-side-side congruence postulate, also known as the Sss Postulate. Okay, what it says is this: if the sides of one triangle are congruent to the sides of another triangle, then the triangles are congruent. Alright. Example, here's triangle ABC. Regardless of how I drew them. And here's triangle XYZ. They are marked. Segment AB is congruent to segment XY. Segment BC is congruent to segment YZ. And segment AC is congruent to segment XZ. So since all of those sides are congruent to each other, then by the SSS postulate, triangle ABC is congruent to triangle XYZ. Okay? Now this Cpctc just keeps showing up all over the place. I don't know why. Maybe it's important for you to know that. Know what it stands for. According to Cpctc, then, we can coordinate those corresponding pieces. What are the corresponding pieces? It's very important you get the corresponding pieces correct. Triangle ABC, put it over triangle XYZ. Notice that X and Y has the one mark, so that has to go with A and B. X and Z has the three marks, and so X has to go with the A because the A has the 1 and the 3 next to it. Between the B and the C is the 2 mark. So make sure that when you set these up, you set them according to the corresponding vertices or points so that everything comes up right. Otherwise it messes up. So when we draw our lines, it's pretty apparent that angle A is congruent to angle X. Angle B is congruent to angle Y. Angle C is congruent to angle Z. And that segment AB is congruent to segment XY. Segment BC is congruent to YZ. And segment AC is congruent to XZ. And that's all according to Cpctc because these two triangles are congruent because all of their sides are congruent. Now we're going to do a little proof of one, an example how to prove using SSS postulate. Okay, got here is we're going to give it a figure. We want to prove that two triangles are congruent regardless of how they look like they're drawn. And we want to use the side-side-side congruence postulate known as SSS postulate. Figure we're given is, you've got a figure here with 3 triangles in it. Here's one triangle, ABC. Here's another triangle, DBC, and triangle ABD. And we're given that, and let's mark this thing up, we're given that AB is congruent to DB. So let's mark this, okay? AB is congruent to DB. And then we're also told that C is the midpoint of AD. Well, what in the world does that mean to us? C is the midpoint of AD. Well, if something is the midpoint of a segment, if a point is the midpoint of a segment, then it bisects that segment. It's a segment bisector. Anything that is a segment bisector cuts it in half and creates 2 equal or congruent pieces. So C cuts segment AD in half and creates 2 congruent segments. And those congruent segments are right there. Okay? So that's what we can come out of over here. Alright? So let's see how we might be able to prove this and see what happens. Number one, we're given that AB is congruent to DB. Okay? That's just given to us. Now what we're trying to do is we're trying to get 3 sides. Well, there's one of them. Okay? There's one of them. Now we're also told that C is the midpoint of AD. Well, C, midpoint, AD. It's given. Well, what does that mean? Well, we've marked over here that that means to us that segment AC is congruent to segment DC. Now notice I said DC instead of CD. Why? Because I want to keep the corresponding points and vertices together. A corresponds to D. C corresponds to C. Okay? So this is actually corresponding. A corresponds to D. D corresponds to C. How do we know that? Well, we're trying to prove triangle ABC is congruent to triangle DBC. So what lines up? AD lines up, so A needs to go with D. So that's why we're doing that. Well, guess what? There's another side. Why is this? Plano definition of midpoint. Okay, so there's two of them. How in the world do we get our third? Well, don't know if you remember, but there's a property of algebra that we moved into the geometric realm. Three properties, as a matter of fact, quite a few properties, as a matter of fact, that we moved from algebra into geometry. I call them 1, 2, 3, RST. 1, reflexive. I look like myself. I'm equal to myself. 2, identical twins are equal to each other. Joe looks like and is equal to Jim. Jim looks like and is equal to Joe. Identical triplets are equal to each other. Joe looks like Jim, who looks like John. Reflexive, symmetric, transitive property. One entity, reflexive. So what side is equal to itself that we need? Segment BC is congruent to segment BC. Why? Reflexive property. Okay? Wow, look at that. Side, 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 I have my three sides. So therefore, have we proven this? Yes, we have. A, B, C is congruent. Whoa, that's a little weird. Is congruent to triangle D, B, C. And again, notice that we set it up correspondingly. The corresponding vertices or points. Why is this congruent? Well, side, 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 postulate. Okay? Now, we could also extend this a little bit. Let's say that they didn't want us to prove this right here, but they actually wanted us to come down here and prove this point. That angle A is congruent to angle D. Well, let me show you what our next statement is. Our next statement would simply be angle A is congruent to angle D. Why? Cpctc. That thing just keeps showing up, doesn't it? Cpctc just keeps showing up. So once we have proven that the two triangles are congruent by one of the postulates we'll be using, then all the corresponding pieces of those triangles are congruent. How? By Cpctc. Okay, it's proof. Two triangles are congruent given that their sides are congruent.